global existence of solution for the initial value problems. So far what we have discussed is existence and uniqueness. Okay, we discussed existence and uniqueness. Some ideas from mathematics, the basic mathematics or basic calculus, how we can use to do these things. Okay, so the third important one is continuous dependence. Is continuous dependence.
Sir?
Yes.
Sir?
Yes.
Your screen is not visible.
Oh, screen, I didn't share it. Oh, I forgot to share. Yeah. Is it fine now?
Yes, sir.
Yeah. Yes, sir. So far we discussed existence and uniqueness, and third important one is the continuous dependence. And what is this continuous dependence? So the continuous dependence, basically we want to say, if I take f prime equals to ftx with x at t naught equals to x naught. Okay. So the continuous dependence is that we want the solution, right? So this is the solution x, okay, depends continuously on the initial values, depends continuously on the data. So what are the data here? The data here is f, which is given to us. Okay, f is data and also the x naught. So what is that means that I want the solution x, okay, to be a continuous function. Suppose why this is continuous dependence is important is when you do any real world problem into a mathematical model, you get a differential equation. But the initial data or the nonlinearity, that this is also known as the source terms. So these things we calculate using some instruments. Say for example, measuring the temperature. Okay. So it is never going to be exact. If you see if you look at if you take a thermometer and you put it at a point, and then measure the temperature and then take it out, and then again you put the thermometer there, then you get a different value. But these two values are close to each other. They are not going to be, it doesn't show that once you have 90 and it doesn't show 104 or something like that. So it shows if you have 95, then it will be 96, or if you have 99, it will be, next time it will be 99.5. It's not going to be far different. So that is why these data, okay, so the data points, when you measure, they have an error. Okay, so we don't want that this error will lead to a big difference in the solutions that we find. Okay, so that is why, so the error in the measures, error in the data should not lead to big difference in the solution. That is the whole idea of this thing. So this all these 3 points, existence, uniqueness, and it is known as the Hadamard's Wilposeness. Okay, so this all these three points are covered in this. Then is one is existence. The problem should have existence and it should have the uniqueness. Okay, and the continuous dependence. So basically what we are looking at is precisely, let me write, if x prime equals to f tx with x at t naught equals to x naught, and take another problem, or take y prime, which is equals to f ty plus small epsilon with y at t naught equals to x naught plus delta. So that is the values between these two things. The data is perturbed by an epsilon and delta. Okay, so what we want is, okay, what is the meaning of continuous dependence? Means that as epsilon and delta goes to 0, we need xt minus yt should go to 0. Uniformly. Uniformly in a need not be for all times, but uniformly near the initial values. Okay, near the uniformly in a neighborhood around x naught, t naught, in a neighborhood around t naught. So this is what we need. That is what this is a continuity. Continuity is that if I write x depending on this f and x naught, where these two things are going to 0, okay, the difference between them is also going to 0. So this is the meaning of that. This is a continuous function. Okay, so if I define the data to the solution, okay, a map. Okay, now that map is going to be a continuous function. Okay, so that's the meaning of it. So we basically want to see that as epsilon and delta goes to 0, the difference between these two solutions also goes to 0. So how is this done? This is done through the so-called the Grunwald's inequality. It's a very popular inequality. Of course, you will see the this itself, the study of Grunwald's inequalities, the Grunwald's inequalities and their generalizations and so on, that itself is a big research area. But the basic idea of the Grunwald's inequality starts from here. This is the first fundamental Grunwald's inequality, which comes in the first order differential equations. Okay, so what it says is let x be a differentiable function and suppose mod xt is less than or equals to delta plus some k times t naught to t of mod x s ds plus epsilon times t minus t. Okay, suppose this happens, then the following is true. Mod xt is also going to be less than or equals to delta by k into exponential of k into t minus t naught plus epsilon by k square to e power k into t minus t. Okay, so basically this shows us that if you have the first inequality, this inequality, then the second inequality follows. Okay, so now you can go back to your suppose assume that this is true, and then you look at these two equations. Okay, so this is the proof. I will come back to this. This is the theorem. So now use this. Go back to our problem. So you have the xt, which is equals to x naught plus the integral of t naught to t of f tx to ds, right? This is one. And the other one, yt, is satisfies x naught plus delta, that is the initial value, plus t naught to t f of s x plus epsilon. So these are the two problems that we considered here, x and y. Okay, from here, from start. Okay, so from start. Because if they satisfy the differential equation, they have to satisfy this integral equation also. So now you subtract these two things, that is xt minus yt. This is going to be, you have the x naught minus or yt minus x naught. You may write yt minus x naught also, it doesn't matter, because we are going to ultimately take absolute value. So this is going to be delta plus, you have the t naught to t of f of s sy plus epsilon minus fsx. Okay, so now you take the absolute value. If I take absolute value here, it's going to be less than or equal to delta plus, this becomes absolute value. Okay, and you see that here you can write this as sfy minus sfx plus epsilon. Okay, so this is see, this is going to be now less than or equals to delta plus, you have the k, which is the ellipsis continuity, times mod y minus x plus epsilon times t minus t. See, this is what we have, mod y minus x, and that is what we have in the first equation here. It is this for x and this is for y minus x. Therefore, y minus x will be less than or equal to delta by k into e power k into t minus t naught plus epsilon by k. Therefore, you see that here, as delta and epsilon goes to 0, mod xt goes to 0. Okay, I can take mod t minus t naught in a small interval around t naught. Then you see that as epsilon and delta goes to 0, mod xt goes to 0 uniformly, because exponential is going to be a bounded function in an interval around t naught, in a bounded interval around t naught. Okay, so that is how this thing is used. So this Kronwall's inequality is important in getting the continuous dependence. Of course, it can be also cleverly used for getting the uniqueness that you think about. Okay. Okay, there are many situations and integral equations and integral differential equations. People use these Kronwall's inequalities for getting the uniqueness. Well, so now let's see how to prove this. Take for example ET, which is t naught to t or x sts. Okay. Then you see that this e prime t is equals to mod xt. Okay, and we know from the hypothesis that this is less than or equals to delta plus k times this one is et plus epsilon times t minus t. Okay, so you have a relation that is e prime is less than or equals to this one, delta plus ke plus e into. So now we can try to make this. Okay, so we can. So if you see this is we can write this as e prime t minus k et. Bring that term to this side, and therefore we get this to be less than or equals to delta plus epsilon into t minus t naught. Okay, so now we can, the idea here is to make the left hand side an exact differential. Therefore you multiply by exponential of minus k t, and this remains et, and the derivative of this, that is going to be your left hand side. Okay, so this is remains the same, e power minus kt plus epsilon t minus t naught into e power minus kt. Okay, so now from this one can integrate from t naught to t. Okay, so when you integrate it, then you get the inequality. So it's not very difficult. If you have difficulty in doing the this integration, then you tell me. I will send my work out. Okay, it's not difficult, just an integration. Okay, so the result follows. Okay, so what we had earlier was so application of this is when you apply, you get mod xt minus. Okay, so mod x minus y is less than or equals to delta e power k into t minus t naught plus epsilon by k square into. Okay. So what I meant to say is that you take the maximum over t lies between the interval that we had, t minus h to t plus h. Okay, it's a where so you had
delta by k.
Delta by k. Yeah. So where you had the take the maximum over this, then you get the maximum over this mod t minus t naught less than or equals to h of mod x t minus yt. Okay, so that is where you get the uniform delta by k, and when I take the maximum over this thing, then this is simply a bounded function. Okay, see that the mod t minus t naught less than or equals to h times e power k into t minus t naught. So this is now going to be a bounded quantity. Similarly, the other one. Okay, similarly the same constant which comes here. So these are the two constants. Okay, therefore the maximum of this is going to be less than or equals to delta by k into a constant plus epsilon by k square into another constant. Okay, therefore as delta and epsilon goes to 0, this maximum goes to 0. Okay, so as delta and epsilon goes to 0, the maximum over mod xt minus yt this one goes to 0. So this is the meaning of uniform convergence. This is the meaning of uniform. It's not uniform convergence. The uniform convergence in epsilon and delta. Uniform in epsilon and delta. Okay. So that is about the continuous dependence. Do you have any questions on this? Okay, now let's go on to some more analysis to see that to look at the limitations of this Picard-Lindlof theorem, or the so-called Picard's theorem. So to see this kind of things, in mathematics, we want to understand in a very abstract sense, so that we can easily identify what are the limitations of these methods. Okay. So the Picard actually considered these Picard successive approximations, and he proved this convergence. I mean, of course, parallelly the Lindlof little later. They showed the existence of a local solution. And then came the Banach. Okay, he came out with fixed point iterations. So he basically took the ideas of the successive approximations and showed that these things actually can be done in a more general metric spaces. Okay, so called the complete metric spaces, and that led to an idea by Peano to relax the condition of Lipschitz continuity to prove the existence of solutions. Of course, I will tell you once if I prove these things, then I will also tell you the some of the more finer analysis which are more recent, say the ones which started in 50s and 60s of 1950s and 1960s, where this simplifies this many of these Peano's arguments also, okay, to a large extent. So that gives actually the very broader picture of how these things, existence, uniqueness, all these things can be, one can expect to prove. Okay, so that's the beauty of this abstractness. So by now, I guess all of you know what is a complete metric space. Space setup, but let us do this way, the way it was done in the Banach point theorem. Okay, so we define what is called a contraction map. By chance, is it defined for you in your real analysis course?
Sorry, sir. Please. One
Sir,
second.
Huh?
sir, your voice is breaking.
Sir, your voice is not
My voice is breaking. I'm asking if this contraction mapping theorem.
No, sir. Not here.
Not done. This is called a map from X to X. X is a metric space. Let me take it to be as a definition. You can define it anywhere, but for us, we are only bothered about complete metric spaces. Generally, you can define in any metric space. If there exists a constant L, okay, which is strictly less than 1, such that the T of Tx, Ty is less than or equals to L into xy. So this is true for all xy belongs to X. Okay, so if such a thing is true, then we call this map T a contraction map. So this L less than 1 is very important. Okay, then only we call it as a contraction map. So you see that what's basically happening is that the distance. Yes. What is? D is the metric, man.
Any T
T is a map, no? T is from X to X. It's a map.
Yeah, yes.
That's what I'm writing. T is a map from X to X. So this basically says that the contraction means that the distance after taking the mapping is actually becoming less than the distance it has before. Right? So that's what this definition says. That's the also meaning of contraction. Okay. So what is the theorem here is this is also known as Banach's fixed point theorem. So if X is a complete metric space and T is a contraction, is complete and T is contraction. T is a contraction map. Then T has unique fixed point. Okay, unique fixed point means that what is the meaning of fixed point? That means there exists a unique X in X such that Tx equals to X. There is a unique X so that Tx equals to X. So this one, if you might have seen in your basic calculus, recall your calculus. So in case of functions from the intervals, this is what we do in the calculus. If this function is contraction, okay, if this is a contraction, and if it is just a continuous function, course, contraction, from the contraction you can show the continuity. Then f as fixed point. Of course, you can also show the unique fixed point. So why the this comes? We, in case of just this is only a real line case. So, okay, we are only taking an interval where the range is also from 0, 1 and the domain is also 0, 1. Okay. So in this case, the proof simply comes by the intermediate value theorem. For example, you take the function gx, which is equals to fx minus x. Okay. So in this case, you see that at 0 and at 1, right, by intermediate value theorem. Intermediate value theorem. What is that? At g at 0 is going to be f at 0. And you know that f at 0 is greater than or equals to 0 because the range is also 0, 1. And also look at g at 1, which is going to be f1 minus 1. And you see that f at 1 is less than or equals to 1, therefore this is less than or equals to 1. Suppose if, sorry, this is less than or equals to
0.
0. So if you see that if g of 0 equals to 0 or g at 1 equals to 0, then you already see that there is a fixed point, right? F at 0 or f at 1 is 1. Therefore, we assume that g at 0 is greater than 0 and g at 1 is strictly less than 0. Right? Otherwise, you already have a fixed point. So if it is greater than 0 and less than 0, you know that by intermediate value theorem, there exists a point x where g at x equals to 0. Right? So call it as x naught. So that is nothing but f at x naught equals to x naught. That is the fixed point. Uniqueness is not difficult. I will show you when I do the metric space, then you see that how to show the uniqueness in this. So basically the existence of the fixed point is it's basically the intermediate value theorem in case of calculus, in case of when we have just the interval. But in case of a general metric space, we assume that other than this contraction, we assume that the completeness, because without completeness you can't expect this. We'll see in your real analysis course why the completeness is necessary and things like that. So what is the idea? The idea is basically the same as what we did in the Picard iterations.
Hello.
Yes?
Sir, only continuity is given there, not
Continuity?
contraction.
Contraction is of course necessary. I'm saying this is the next fixed point theorem is continuous and contraction, right?
तो वहाँ पे नहीं सर, यहाँ पे जो आपने रिकॉल लिखा है,
किसमें लिखा है?
तो यहाँ पे if f is
Yeah,
0,
so
1, 2.
That's right. So for existence, you don't require, but uniqueness, you need the contraction.
Okay.
That's why I said the contraction. When I do for the metric space, we will see what is the use of this, how to do this contraction. I mean, when there it's not difficult. If there are two fixed points, then you can just do it. They're not very difficult. It's not just write what is the meaning of fixed point and then subtract them and then see, use the contraction, then you get. Okay. Okay. So the idea of the fixed point theorem, the Banach's fixed point theorem, is basically the same what we see in case of the Picard iterations. See, they define xn equals to t xn minus 1 with starting with any point x naught. Okay, start with any point x naught, and then you write x1 is tx naught, right? So it means to say x1 is tx naught and x2 is tx1 and so on. This is what we did in case of Picard iterations, right? So Picard iterations, what we did, if I didn't write t, but we wrote xn equals to x naught plus t naught to t f of s comma xn minus 1, right? So if we write this as our t, then we have it. That's what it is. Right? So basically the idea is the Picard. These are also these iterations are known as Picard iterations, successive approximations or Picard iterations. Okay. So our aim is to show that this is sequence xn converges to x, and eventually this x becomes my exponent. So since we also assume that x is a complete metric space, so the idea is to show that xn is a Cauchy sequence. Okay. So write what is d of xn minus 1. How do we, this is how we show the Cauchy sequence, right? So in case of real numbers also, we first estimate the difference between the two consecutive numbers, and then we take any two numbers and use this consecutive numbers to get that, right? So it's the same thing that we use here. So just use what is the t of xn. Xn, we know that t xn minus 1, and this is t xn minus 2, right? So we know that this is by contraction, this is going to be less than or equals to L of d xn minus 1 and xn minus 2. And continue this. Again, write xn minus 1 as, right? So t xn minus 2 and xn minus 2 as t xn minus 3. That's all. And again, you will get 1 L square, right? L square of t xn minus 2 minus 3. And continue this. L power n minus 1 into okay. So we got the distance between two consecutive numbers. Once if we have this, then we can write using this. We write d of xn and xn for any m greater than n. Take any n, m and n, where m greater than n. So use the triangle equality to write this as xn minus 1 plus xn minus 2, and so on up to x n plus 1 to x, right?
xn minus 1.
N minus
M greater than n I am taking, so it's going from n to n plus 1 up to m.
Sir, in the last dxn minus 1 xn.
Now n minus 1 will be less than n, right? So we want, see, I'm taking m greater than n. M greater than n means that I am having the
Okay,
n,
sir. Okay, sir. Yes.
n plus 1 and up to. So there's a typing error in the notes. Don't look at the. That's why I always say that you have to be attentive in the class. There are some errors normally happen when you type the notes. Right. So this is going to be. Now apply the previous step, because these are the now consecutive numbers. These are the consecutive elements. Right. These are the consecutive elements now. So here we can apply now the.
But
so
sir,
this
it is by triangular inequality, metric spaces. So
what metric spaces doesn't have triangular inequality.
yes, sir. D of xm minus 1, then d of xm minus 1 m minus 2. So here should be d of xn minus 1 xn.
No, you have to see what are the elements that you have, right? So you are starting with m greater than n, so you have xn, n plus 1, right? And goes on up to xm now, xm minus 1 and xm. That's how you have the elements. These are the elements you have between xm and xn. the distance between xm and xn, I will only introduce these things, right? It's going to be less than or equal to distance between these two.
xn minus 1. D of xn minus 1 xn. Last one.
Why?
Yes, sir.
Why?
So by triangular inequality, we can prove this.
But I don't have the xn minus 1 here, right? So I have the elements xn, xn plus 1, xn between xn and xm. I only have these elements. Why I want to put xn minus 1? Xn minus 1 is here. But I'm looking at only the distance between these things, right? So I will write xn, xn,
Okay.
xn minus 1, xn minus 2, like this one, xn plus 1, like xn. I mean, you can write one more term, but it's of no use. You can write as many terms because it's only less than or equals to. Okay, so you just plug in those inequalities what I had earlier. So you get this to be less than L power n minus 2 into 1 minus L. Basically, you write all the terms that you get L power n minus 2 into 1 plus L and L plus L square and blah blah blah. Since L is less than 1, it converges, the geometric series converges, and therefore we have this. Okay. And you see that this is now a fixed constant, and this is something which goes to 0 as n tends to infinity, because L is strictly less than. So you see the importance of L being strictly less than 1. So this is the, if you have done your, if you remember the things in your calculus, this is what we do in case of sequences also. When you try to show the sequences, some sequence to be a Cauchy sequence, okay, there are many examples. Basically, this is what we try to show. If you have the distance between consecutive numbers, if they are compared like this with L strictly less than 1, then we show that this xn is a Cauchy sequence. So it's the same thing that is happening here. The same calculations what we do in case of sequences for mod, we are doing here with D. That's all. Therefore, xn is a Cauchy. Okay, therefore xn is a Cauchy sequence which converges to x. Okay, which converges to x.
Yep.
Yes.
Here we
Yes.
show L minus 2 into L 1 plus L square up to क्या जो ये टर्म था L to the power m minus n plus 1 as mentioned in notes. So first we take n finite sum, then after we have to go for infinite
Yeah,
sum.
so you take the finite sum and then extend it to infinite because you are adding more and more terms only, right?
या फिर हम ये कह सकते हैं कि n tending to infinity पे ऐसी डायरेक्ट 0 चला जाएगा विदाउट ये लिखे हुए.
No, not that. No, not that. Not that. See, there are certain things which you can do and certain things which you cannot do. Okay. So use the previous inequality here. Xm and xn minus 1 is going to be L power n minus 1. So this is going to be less than or equals to L power m minus 1. Okay. Into d of x1 x0 plus what is the next one? L power m minus 2. Okay.
Yes.
And so on up to L power n. Okay.
Yes.
Times the d of. So here take the L power n a common factor. You get 1 plus L square up to L power m minus n.
M minus plus minus 1.
Right, times d of x1 x0. Now you see here this term, there are only finitely many terms here, so that is going to be strictly less than. You keep this one as it is, L power n, and this one you replace with infinitely many terms of the geometric series, because we are only adding more and more terms. So what I will get is strictly less than, and we know that this is nothing but L power n by 1 minus L, okay, times this constant. So this is now a constant, and this is a constant, and this L power n. So this whole thing goes to 0 as L is strictly less than 1. Because L is less than 1, the geometric series converges to 1 by 1 minus L. And since L is less than 1, L power n also goes to 0 as n tends to infinity.
Yes, got it now.
Yeah. Okay, so this is how you show the sequence converges, and you have the sequence converges. So therefore, this is let me take the, and it is a complete metric space. Therefore, it converges to X. Okay. Now, since xn is t xn minus 1, and t is now continuous, take the limit on both sides. Okay, so this is x, and this side it is going to be x. Okay,
Yes,
so
sir.
that means that tx equals to x, which is a fixed point. So how do one show the uniqueness? I'll leave it to you to do this, or you can do it. Suppose there are two. The same thing what you can use it for in the real case, in the sequences case. Okay, if there are two fixed points. Okay, so write d of xy, which is d of tx ty is less than L times d of xy. Therefore, since L is less than 1, this implies that x equals to 1. Okay, otherwise this cannot happen. You can write less than or equals to, but L is less than 1, since L is less than 1.
Yes, sir. Got it.
So you see that here what we are basically getting is that uniqueness requires the contraction. Okay, just to keep this in mind, I will tell you later. That means that if there is still possible to get the fixed point, even if you don't have the contraction, but you may have to ensure the some kind of convergence of this sequence, right? So that because this sequence can be defined, and this sequence is can show this sequence to be contraction. The sequence is if we can show, I don't know how it is possible, but if we can show that the sequence is a convergent sequence, or if you see the sequence need not converge as a whole for getting the fixed point. Even if you have a subsequence which converges, still you will get the fixed point. So these are some of the ideas that we will use later, that the convergence of the entire sequence is not necessary to get the fixed point. That is one observation. And the other one is that contraction is required possibly to show only the uniqueness. Okay. So now let's go back to our, okay, so now it's not time, the time is over. So I'll do the next time, we'll see how the Picard's theorem can be proved first, and then we'll go to some relaxations of this fixed point theorem. Yeah.
Can you please write the last two statements which you said?
Yeah, so last two statements I said is that from the proof, if you see, it so appears, I don't know if it is true, it appears that the contraction is possibly required to show the uniqueness. Okay, and another place what we used is the convergence of this, right? But here I am showing the convergence of the entire sequence. Suppose I don't require this. Suppose if we have a subsequence which converges. Okay. Suppose if a subsequence converges, then also I will have the fixed point. Right? Because if a subsequence converges also I will have fixed point, right? So if you see what is the xn. So if you have a subsequence of xn, say xn k, which converges to x. Suppose if this is possible, then I can take the limit in this, right? So then also you have the tx equals to x equals to tx. It's possible just by taking the limit. So somehow if I can ensure that this xn has one subsequence which converges, okay, then I can possibly remove this contraction, the idea of contraction. But how to ensure that there is a subsequence, at least one subsequence, which converges? Okay, so this I will discuss later, because we are relaxing quite a bit that we don't require the entire sequence to converge. We require only a subsequence which converges to get the fixed point. That is enough. If you
Matrix
don't
have to be bounded, then it have मैट्रिक्स अगर बाउंडेड हुआ मैट्रिक अगर बाउंडेड हुआ तो फिर हो सकता है
bounded over, that's what we are going to discuss, right? So in a boundedness, if it is there, then you have a subsequence which converges in the real line case, right? That is what
Yes.
you see what is called the Bolzano-Weierstrass theorem.
Yes.
So whether the Bolzano-Weierstrass theorem is true in a metric space, that we will see. Okay.
Thank you, sir.
That's where the answer lies. You are correct.
Yes.
Okay. We'll see tomorrow.
Thank you, sir.
Thank you, sir.